I want to give a little context on what we're doing today. If you remember, sometime last week, we went through this process of measuring and testing a couple of magnets. We got a value for the weight of an individual magnet, so we know the mass is 3.27 grams according to our calculation. What we did then was we came up with the force that the magnet would be exposed to from the Earth's gravity. So all we did was use uh, our mass in kilograms, and we multiplied it by the constant for the Earth's gravitational pull, and we end up with a number of newtons. So when the magnet is sitting on a table or in a static condition, then it's experiencing a downward force of 0.032 newtons. So then what we did was to get some other characteristics on the strength of the magnet. We came up with kind of a thought experiment where if we could have an anchor magnet that's fixed in position and somehow allow the what we call the floating magnet to be able to hover above, then we know that when the polarities are aligned, they repel, and there's going to be a condition where the forces will be balanced, and that's going to reveal a distance. So what we did was, if you remember, we came up with for one magnet or two, three, four, or five stacked on top of each other, we measured the distance from the center of each magnet where that reached equilibrium. As you remember, it was kind of a complicated measurement with the equipment that we had. There's lots of room for improvement, and maybe that's something that you would be considering today. So what I wanted to do was, now that we have that defined, we have some actual measured data that we took, let's go ahead and go into a simulation and see if we can reproduce this with the simulation. I've taken the time to set everything up for you already. So all I really want you to do is, get into the solver so we can run the calculations and we can do a comparison to this. Okay, the next task is to move over to the server. So you should be doing this probably through your Edge or Explorer window. I'm using the app. You can see here I'm logged into TPS-CTE. The first thing I want you to do is go to the desktop. The link that I gave you to the folder for Magnet Board. So I'm scrolling through my OneDrive. I have already shared this with you on Teams and on Schoology. So as I look through my directory tree here, here's this magnet board. You'll see things that you've already been looking at, some discovery models, the specification for the magnet board. I want you to look for this magnet now. So it's a new electronics desktop project. You'll also notice that it was done, it should give a stamp of the version. This is going to be well, I guess I'm wrong about that. I thought it would. But either way, what I want you to do is make a local copy of this. So one way to do this is to grab the magnet file. If I hold Control, or what I can do is just right click and I can say copy. And I'm on my desktop for the server. Yours will look similar, but maybe a little bit different. I'm allowed to put local copies on my desktop, and I think it's going to make the performance a little bit better. So when I right click and say paste, you should get the same thing. Give it a second probably to download and sync up, and then once that happens, you'll see it right there on the desktop. With that, I want you to go to Electronics Desktop through the Start menu, and if you scroll down, you will see the ANSYS folders, and the new one that you're going to see is ANSYS EM Suite 2023 R1. I'm going to pause, or I should ask you to just go ahead and pause this if you're having trouble finding it, but you're looking for this guy right here, ANSYS Electronics Desktop 2023 R1, inside that folder. So pause the video while you hunt that down, and as soon as you do, please go ahead and open it. It might take a second, and it's going to ask you some defaults. I've already answered them on my side. Just click away at all the default settings. It's really not going to matter, and eventually you'll get the common empty screen that you see here. Mine is showing up with Project 3 as the default. What I'm going to do now is go ahead and open that file that I dropped on my desktop. So I go to File, Open, and I'm going to click Desktop here. And the only one that I have available on my machine right now is this magnet. I'm going to give you a second to get a similar setup as to what you see here. So when your project opens, hopefully you are seeing it looking about the same. Remember, you can turn the progress and the message manager window on with these buttons down here in the bottom right. If you see any other windows that you don't see on my screen right now, just look for the X mark and click them away. And I'll give you, I would say, go ahead and pause this video if you need a second to get caught up to verify that you see what you have. So you see the same thing that I'm showing here. And as soon as you do, we'll move on to the next step. So pause this video as needed. Okay, I assume we're all ready to go. So what I did want you to do is verify one thing, or I should say maybe you have to make your own settings. I'm going to go to the simulation tab. And remember this HPC options. We looked at this before. We're on the server, and this basically tells us how many cores we're going to use. You guys can decide if one of you is leading this effort right now and the rest on the team is just kind of following along but not running the simulation, then I would say go ahead and grab all cores. I'm using all 24 cores right now. So if 2 or 3 of you are going to run the simulations together, choose an appropriate setting, maybe 8 cores each, that something like that. But choose as many as you can to get the efficiency up, so this thing will solve pretty quickly. Okay. So with that, I'm going to say okay, and I'm gonna go ahead and start running that simulation, and I'll try to describe what's happening. I should have stayed on the simulation tab there. With that done, I'm just going to hit the Analyze All button. So please take a minute to verify that you see something similar here. You should be getting the progress bar is going through if you remember the adaptive passes, you should be seeing this marching along right now. You shouldn't see any errors over here. If you do, pause the video, try to get your bearings, get things figured out so that you can get to this point. And then once you do, then we'll kind of march along, and you can listen to me describe what's actually happening and what our setup is here. So take as much time as you need for this. And if you come back, then we're ready to get moving along here. So what I want to show, a quick description of what we have set up here. If I expand my project tree, you will see a lot of things have been defined for you, right? We wouldn't be able to run the simulation if that wasn't the case. We'll talk about this later in the week on Friday. Right now, I just want you to get results because the objective is let's look at before I go over the project tree, let's go over the modeler tree. You can see the components that we have in here. There are these 2 things under solids, and they have this kind of this alphanumeric name, which I'm about to describe. But I want you to pay attention to the fact that we've got 1 fixed magnet and we have 1 floating magnet. So if you want to make this look the way it did in our whiteboard, then our floating magnet is the one on top. So our fixed magnet is the one that's on the bottom. And these are both defined this particular material value. So what I want to do is right click on that material, and I'm going to go to properties. And this is a value that was built into our library. It stands for neodymium. The 30 is corresponding to, I believe, a temperature where that measurement was made. Magnetic materials can vary quite a bit. And we're not going to go over this in detail right now. I just want to slide over so you can see some of these values. We've got a permeability that's been defined. There's a bulk conductivity. There's something called a magnetic coercivity. These are all things that are just defined in the material values. So we can look up the permanent magnet like we did here, and here are the values that have been defined. You can also see a structural component called Young's modulus. The other thing I wanted you to be aware of is that when I go into this button, View and Edit Materials, you can also see that there's some things that were defined under magnetic coercivity under the vector setting. So what I wanted you to pay attention to is the fact that I've got this magnetic coercivity Z component unit vector of -1. What that is saying is that we're telling it basically what the polarity is of the magnet. And if you remember, we did the tabletop testing where we decided if they repelled each other, they were like-oriented. So it's arbitrary if it was the North Pole or a South Pole. This is basically determining the direction of that polarity. So If we made it -1, it's pointing, North Pole might be on top, south on the bottom. If we made it +1, it would be in the other direction. So this is one way that we can control whether or not the magnets are going to attract each other. So if you, I'm going to cancel out of that. Let me cancel out of the screen. You should also keep in mind, we're going through this parametric solution that I'll describe in a second. But the fact that both of these magnets are in the same material definition means not only are they the same type, the neodymium, but they are also of the same polarity. So for that reason, they should be repelling each other. So I also wanted to show you that there's on the left-hand side here, as I go through the project manager, there are these parameters that have been defined. The parameters are basically force and torque. The ones that we're going to be looking at right now are going to be the force parameters. So we have one. If I highlight on it, it'll show how that parameter is associated with the object. So I can see force underscore float corresponds to the one that is indeed floating, and then force underscore fixed is a parameter that corresponds to the one that's actually anchored. Okay, so this will be important in a second. You'll also notice as I back up and highlight that air volume, you guys are familiar with this. We have the region, the vacuum region. So this is just the space in which these things are, the whole solution is being solved. Our magnetostatics solution is being solved. So that's the only geometries that we have in this case. The other thing that you've noticed is that there's a meshing operation that has been applied. We did a meshing operation back in electrostatics. The same sort of thing has been done here. If you click on properties, actually not properties, but if you click on select assignments, you can see the controlling of the mesh has been applied to the magnets themselves to try to get a good accurate solution here. So that's already been set up for us. We also have the analysis set up. I'm not going to go through those details right now. But I wanted you to remember the conversation that we had on parametric modeling. We did this for the antenna. We also are doing it here. So you can tell right now it's going through these multiple solutions. 6 have been solved. It's got 8 remaining. What it's doing right now is going through this. If I open up Optimetrics and look at parametric setup, when I double click this, you'll see that there's this variable called dfloat that has been defined, as you can see here. So there's been a linear step from 10 millimeters to 50 millimeters in 10 millimeter steps. And then there's another segment of this that's much, it's less coarse of a step. It's 1 millimeter steps going from 0 to 10 millimeters. If I click the table tab, you can see all those values. So what's happening here is that this value, this variable called dfloat has been defined, and it is running a solution for every instance that you see here. So let me cancel out of this. One way to see what's happening is that if I keep the solution going, but if I right click on parametric setup, I can now say animate, and when it asks you to select a drawing, it's not going to matter what you choose, just say OK. And then the animation, you can just say OK to that as well. And what you're seeing here is an animation of the settings that we gave it for a parametric solve. So here's our variable, dfloat. So when dfloat is 0, you'll see as it cycles through, it means that the two magnets are touching. The distance is 0. So for us, on the whiteboard measurement, if you remember, the way that we set it up was we measured from center to center. So when dfloat is 0, the number for us was actually 15 millimeters because it's the radius of the anchor magnet plus the radius of the floating magnet. So I want you to keep that in mind, but what's happening is that the calculation is being made for all these different distance settings. So it's got 4 more to get through. So if you chose all the cores, you should be moving along about as fast as this. I'm gonna give you a chance to pause the video because I need you to have a result here that you're going to look at and discuss shortly. So I'm going to keep going. I'm going to let mine solve while I pause, and hopefully yours is moving just as fast, and you're able to get this point. So once the solution is complete, then I want you to hit play again, and we'll talk about the results and what I'm asking you to do today. So my result is complete. I still have it moving in animation. I'm going to go ahead and close that window. And what I want you to go to now is the results section. And there are two tables that were set up. We haven't really talked about tables, but you'll be able to figure this out on your own pretty quickly. I'm going to look at the force table. And what I'd like you to do is you should recognize that this is populated. Hopefully it's not grayed out. If so, something happened to your simulation. I'm going to double click on force table 1, and it brings up exactly what I expected. I've got my parameter here, my variable, I should say, so d float. So remember, 0 is when the magnets are touching each other. So for us, that distance from the centers would be 15 millimeters. So make sure you do the appropriate adjustment when you go through here, because what I'm asking you to do is to see if you can pull a number out of here that validates the test that we did. So go back to the whiteboard. I'll go ahead and switch over real quick. What I'm asking you to do explicitly is go look at the measurements that we had previously completed, and you should find that somewhere in our simulation, remember we're doing a stack of just one right now, but we found that we were able to reach this force of 32 millinewtons when we were at 2.25 centimeters for a distance of separation from the centers, right? So can you look at that table and do a comparison and see if the simulation result is agreeing with the force that we're actually measuring, that we actually measured in the classroom? So that's really the goal today, is to do that, and I would encourage you to make any sort of changes or manipulations to the project as needed to try to get these results to agree. Maybe you want to do a better spacing than what we had done before. Totally up to you. We're going to talk about this on Friday. So you might even be interested in seeing if you can do a stacking of magnets. So can you move an anchor magnet and place another magnet on top of it to represent this condition? I would certainly be encouraging that if you could do that to see if you can validate that measurement. But what you're ultimately looking for is to see if you can pull the distance out and see if you can find the fixed force. Everything is right in front of you. We're not going to worry about it. I believe we might be showing torque on this. We're not showing torque on this table, but you should be able to verify that the fixed force magnet is going to be equal and opposite the number of the floating magnet. As you scroll out here, you'll be able to see that these numbers should be aligning quite well. So that is your task for today, and I look forward to going over this model in a little bit more detail and see how you did on Friday. Good luck.